And I'll be the next speaker.
Так, ну я представляю коллектив.
I represent a team of contributors. My presentation will be devoted to designs made at MEGAG's Department of Photogrammetry. We're talking about calibration of long focal length cameras. First, let's determine why we need to have this category singled out. That's because they are peculiar in a certain way. When we calibrate cameras, we check the distortion of lenses, the coordinates of the main point, and focal length. So the focal length in long focus cameras are those that have length exceeding the frame size by 1.5 or 2 times. Here we do a resection, and this resection point is not a reliable solution, unlike wide-angle cameras, as this picture shows. So the main idea here, when we calibrate cameras, we use the test object. This is our cathedral test object. For wide angles, it's better suited for wide angle, and for long focal cameras it doesn't work out, because as we can see on the right hand, 2 images, they were taken using the long focal camera.
Clearly enough, with this number of points to do high quality calibration would simply be mission impossible. That is why we came up with this following idea. Why don't we shoot the same test object from the same point of image taking, like here on this drawing. Back. Yes. If we, from the same point S, take a number of images of this test object, will increase the resection point. This is the main idea. But how can we implement it? Because first we need to find in the camera the front point of lens and turn the camera around this point. That was the main problem for us. We found a solution as follows. We took a special tripod for the panoramic imaging, which allows us to move camera and tilt and turn it around. To find this, the sensor plane point, you need to do 2 operations. Hang 2 weights, just like shown on, I keep pressing wrong buttons here. As the first image shows, for instance here, perpendicularly to this image we have the weight hanging, and the second weight, one after another. If we see one line on the image, it means that our frontal plane of the sensor is on this line along the chief axis of the camera. Then we turn it around. Usually we don't turn it around this point, but around some other point on the tripod. If we turn the camera to a certain angle, it doesn't matter which one, then we'll see 2 images of these lines. of the weight lines. If we turn the camera not around the central point of the lens, which is located here. If we turn it other way, we see it in another part of the image, two hanging lines, which means that we failed to find that central point of the lens. Then we tried to turn the camera in such a manner that the axis of rotation would be coinciding with the central point of the sensor plane. Then no matter how we turn the camera, we'll see the same vertical line. Then it means that we found it. Now we do the next stage. We capture a few images here of our test object and start processing it, considering that the center of photography or imagery is the same. For that, we developed a proprietary software which allows us to calibrate the camera on multiple images, calculating each image either as an individual or one single one. For the research on this method, first we developed a number of maquette images. On this slide you can see the characteristics of these images. We have done a total of 9 images. Again, I'm pressing the wrong button here. As is shown on this image, we have one single center and 9 images. Each image contains 128 points derived from different lengths or distances from the object. At the same time, each point was aggravated by some random errors, about 1.001 millimeter. And next, these images were processed by 2 ways. First, it was considered that each image has its own independent center, and then with one single center. And on this slide, we can see the RMS error acquired on the inclinations from the true values of the focal length and the central point of the camera. And you can see right away that if we consider each image independently from each other with their own photo imaging center, then we get such an assessment in millimeters. But if it is a single center, C, the focal length, it is virtually 3 times better accuracy-wise. This is as far as maquette images are concerned. Next, we have experimented with a real camera. In this case, it was Hasselblad with 100 millimeter focal length. Here you can see the results of the calibration. And in this part, of the slide and table, we have results of calibration acquired as if all images are considered to be independent from each other. In other words, each one of them has its own projection centers, and the imagery itself, I showed it to you. This is the real imagery here. 4 images were used of our test object, for which we assess the accuracy level. See, if we look at the assessment, RMS error here from the equalization of this value, if we compare them for individual center and for single center, we will see that the accuracy increase in focal length detection is 2 times better if we consider the photography center as a single point. Moving on, by using these calibration results, we have processed stereo pair of the same test object with 49 points with known coordinates. We decided to do direct intersection angles, and it is quite obvious that the accuracy of z-coordinate detection has increased, if not by 2, then significantly, which means that this method of camera calibration is very worthwhile and for sure increases the accuracy of coordinate detection. I'm talking about z-coordinate now. Now, besides this method, we have also invented such a way to calibrate the camera by using not spatial test object but regular test object. There is nothing new here. The flat test objects have been in use for a while for calibration, but according to our experience, it doesn't always deliver good results. It depends on multiple factors. Instead, we suggest using any flat test object, in this case, say a chessboard of some sort. Doesn't matter. Most importantly, that it has many marked points that can be measured automatically with high precision level. This is the precondition. And this method, its main idea is that a camera is mounted on a tripod, it's fixed, and a series of images are taken with different positions of this test object. First, the test object, in our case, this is a chessboard. It is established in such a way that it occupies the whole field of view. It will be considered a control test object, based on which all other board's coordinates will be calculated, and we move this chessboard to another place in space, and we take another image, and the camera doesn't change its position. All the elements of external orientation of the camera are constant, and we make a series of images, like for instance this series of images. Here we have how many? 1, 2, 3, 4, 5, 6, 7, 13 images. We take 13 images with different positions of this camera, and the measurements are done separately for each image, of course automatically, and then we do processing with the assumption that all the images, all these chessboards were acquired like on the same image, and then we do the processing based on the known formulas. The only difference from conventional approach is that coordinates of the point of the object y, z are determined as the points relative to, or system of coordinate systems of the first flat test object, which is used as a control object. So in our calibration, we have to predetermine the orientation of the chessboard during the imaging. This is the difference. Now we have written our software, and it's being fine-tuned now. I hope that at the next conference we'll report about some more tangible results. Thank you. Thank you. Will there be questions? Can I ask a question? She doesn't speak into the microphone, though. Thank you. Can you please explain, how do you do it like this, that your weights are hanging downwards, right? And the optical axis, how do you compare the two? How is it happening, physically speaking? We have hung a couple of weights to a certain distance from the camera, say to the ceiling. We attach 2 weights. For instance, I'm standing here with the camera, and in that direction I hung up 2 weights. Then I move the camera backwards, and I look at the screen or monitor of the camera to see only one vertical line, to make sure that one of these weights is on the same line as the other. And then I start moving it around. If I see two lines, that it means that the central point is not in line with the rotation point. It can be done quite quickly. It takes much longer to tell you about this. Thank you. Thank you. Any more questions? You tried to use Hasselblad only to calibrate, yes. You remember, Aleksandr, looking at Dr. Reisman, I remember that once Hasselblad was applied in non-calibrated way. Sorry, phase 1 was uncalibrated. Now phase 1 is applied with all the calibration parameters. Have you ever thought about taking long focal length phase 1 and compare your quality of calibration with phase 1 in-house calibration? So far we haven't done it, but it's a very good suggestion, and it is. I would be pleased to participate in such a program if phase 1 is not against it. We keep telling all our users in Russia and CIS countries, whenever they have problems with calibration, instead of sending the camera to us, to Israel, it would be much easier to do it in the MIGAIC lab, and I strongly recommend everybody do just that. If the cameras are not in the MIGAIC laboratory, means that everybody's happy with the calibration then. Actually, we have calibrated cameras even from Israel. People came to us with their cameras from. It was Hasselblad. Yes, it was Hasselblad. Can I ask you a question? This is not about tax. You come from the photogrammetry department of MIGAIC. How many graduate students did you have? How many of them work as photogrammetrists? All of them are photogrammetrists, meaning not many. Not many. Only one group graduated. A group of 25 initially. Maybe 17, 18 graduate successfully. And the last year they already all employed. Maybe we need to expand this department, but it's not up to us to decide. It's up to the Ministry of Education. No, it depends on all of us here, because now we're working with school children and they don't understand the word. And nobody is explaining it to them. Let's unite. In that regard, we do the so-called University Saturdays. Every Saturday, MIGAIC reads lectures for students. We have standing room only, each time. About 6 months. In 6 months, we'll do 2-3 lectures about photogrammetry and the UAVs. So we don't forget about school children. But still not many of them. No, not many. By far not many. But not because they don't want to come to us. It's just because we don't have many vacancies in our department. If the professional community unites somehow and offers the decision makers their decision, then something might change.